Welcome to a new series in which we will be exploring exponential functions. As can be seen here, an exponential function is of the form y is equal to a times b raised to the x. Now to define those variables, a is the scale factor. We won't worry about that too much in this lesson, but it will show up later. B is called the base, and x is the exponent. These two will be discussed quite a bit in the next few slides. Let's plug in some numbers. For simplicity, a is left equal to 1. I have selected a base equal to 2. So y equals 2 to the x. I have left x unspecified because it is our independent variable. It can take on many values, as we shall soon see. So what does it mean to raise a number to a power? Basically, it is repeated multiplication. 2 raised to the first power is equal to itself. 2 squared is 2 times 2. 2 cubed has 3 2's multiplied together. 2 to the fourth power has 4 2's multiplied together. The pattern continues indefinitely. On the left, I have tabulated values from x equals 1 to x equals 10. To the right of the table is a plot of the function. Notice how it starts off relatively flat and then bends sharply upward toward the end. That trend is indicative of what we call exponential growth. Now let's see what happens with a different base. I chose b equal to 3, so the function is y equals 3 to the x. Exponentiation is still repeated multiplication. Since we have a different base this time, our numbers will be different, but the same concept applies. For example, 3 to the fourth power involves 4 3's multiplied together. The same rule applies to any other exponent that is a positive integer. Once again, I have continued the pattern and tabulated those values on the left. To the right is a graph which looks very similar to the one we just saw. It is subtle, but you may have noticed that the curve seems to bend a bit more sharply upward. This effect is even more pronounced with the function y equals 5 to the x. In general, the larger the base, the sharper this upward bend will be. The rate of exponential growth is much faster with a larger base. Now it's time to talk about the laws of exponents. These 7 rules are very important to understand because they show up repeatedly in mathematics. It is not unreasonable to expect a student to commit these rules to memory. However, rather than slavishly remembering these, let's focus on the reasoning behind them. That will make it easier to understand why they work and how to apply them. Starting with the first rule, I have arbitrarily chosen 3 as the base in order to demonstrate this concept. So 3 to the fourth multiplied by 3 to the sixth is equal to 3 to the 10th power. That is because 4 plus 6 equals 10. We simply add the exponents in this case. Numerically, that can be easily verified in this particular case. 3 to the fourth is 81. 3 to the sixth is 729. 81 times 729 equals 59,049, which is in fact the same as 3 to the 10th. That's good, but I wouldn't rely too much on this approach. The whole reason we have this rule is to simplify computation. Let's think more along the lines of exponentiation as repeated multiplication. 3 to the fourth involves 4 3's multiplied together. Similarly, 3 to the sixth involves 6 3's multiplied together. When combined, that amounts to 10 3's multiplied together. That is seen by the regrouping in parentheses in the last line. This was a specific example to illustrate the concept, but the same reasoning can be generalized to any base and any exponents. Now let's look at this rule. I have chosen a base of 5 this time. Again, this could be any number. 5 to the 7th divided by 5 to the 4th is equal to 5 to the 3rd. That's because 7 minus 4 equals 3. Dividing an exponential with the same base, amounts to subtracting the two exponents. In a sense, it's the opposite of the first rule we looked at. Numerically, 5 to the 7th is 78,125, and 5 to the 4th is 625. 78,125 divided by 625 equals 125, which is 5 cubed. It's reassuring that this works out, but once again I would discourage relying too much on this way of thinking about it. Let's bring it back to fundamentals. Exponentiation is repeated multiplication. So 5 to the 7th involves 7 5s multiplied together, and 5 to the 4th involves 4 5s multiplied together. Notice the cancellations in the numerator and denominator. Comes down to basic arithmetic with fractions. That leaves us with only 3 5s multiplied together, 5 to the 3rd power. Again, this was a specific example, but the same reasoning applies more generally to any base and any exponents. If you're not convinced, pick your own numbers and try for yourself on a few examples. Now let's show why any number raised to the 0th power is equal to 1. This isn't immediately obvious. To demonstrate why it is true, we will employ the last rule we looked at, as shown on the right. I have arbitrarily chosen an exponent of 3. Any number b raised to the 3rd power involves 3 b's multiplied together. Having the same terms in the numerator and denominator will cancel, as seen by blue lines. I show 3, but regardless of how many b's you have, they will all cancel. With a few caveats, any number divided by itself equals 1. Simple enough. But the rule we just saw says that b cubed divided by b cubed is the same as b to the 3 minus 3, which is b to the 0. Putting the two together, it can be seen that any base b raised to the 0 is equal to 1. How about this rule? Any base b raised to a negative power is equal to 1 over b to that same power, positive. To demonstrate why this is true, we will use the same rule involving quotients, as seen in the top right-hand corner. We just saw that b to the 0 equals 1. I have arbitrarily chosen an exponent of 3 once again. It doesn't really matter, however. The same reasoning applies to other choices as well. But the quotient rule tells us that b to the 0 over b to the 3rd is equal to b to the 0 minus 3, which is b to the negative 3. Combining the two gives us b to the negative 3 is equal to 1 over b to the 3rd power. Specific case, but the same reasoning applies to other choices of n besides 3. This rule says that the exponent distributes to the individual bases multiplied together within parentheses. I have chosen 2 times 3 to the 4th power. Choose your own numbers if you need more convincing. 2 times 3 is 6, and 6 to the 4th is 1,296. This is the same as 16 times 81, which is 2 to the 4th times 3 to the 4th. Good. So why does this work? It comes back to the fundamental concept of exponentiation as repeated multiplication. Notice in the parentheses how I have regrouped the 2's and 3's. From that, the conclusion is evident. This rule says that an exponent raised to another power is the same as the base raised to the product of those two powers. I have chosen 5 squared raised to the 4th power, which equals 5 to the 8th. That's because 2 times 4 equals 8. 5 squared is 25. 25 to the 4th is 390,625, which is the same as 5 to the 8th. So why does this rule work? Again, it comes back to exponentiation as repeated multiplication. We can regroup the 5's, as I have shown in parentheses. 4 groups of 2 is the same as 2 times 4. It is also the same as 2 groups of 4, or 4 times 2. The order does not matter. That can sometimes be helpful to be able to swap the inner and outer power. Last rule. A number raised to 1 over n is the same as the nth root of that number. In order to show why this is true, we are going to use the rule shown in the top right-hand corner. Notice that the product of 1/3 and 3 is equal to 1. So b to the 1/3 quantity cubed is equal to b. But by definition, the inverse of cubing is taking the cubic root. So the cube root of a number cubed is also equal to b. Putting them together, it can be seen that the cubed root of b is the same as b to the 1/3. The same reasoning applies to other values of n, not just 3. The last line is the most general case. I showed why the rule works when m equals 1. I leave it as an exercise to the viewer to show why this more general case is true. It involves a bit more footwork, but just approach it with the same reasoning as we have applied to the other rules. See what you can come up with. Thus, we have kicked off a new series on exponentials. I encourage you to commit these 7 rules to memory. We will be using them extensively to derive a myriad of interesting results. If you enjoyed this video, please indicate that through likes, comments, subscriptions, and shares. It helps out a lot. I appreciate your support and look forward to seeing you next time.